In this video, we're going to talk about graphing non-uniform motion. So looking at what a graph will look like when an object is accelerating. So we're going to start with a position time graph. And this is for a cart rolling down a ramp. So as something rolls down a slope, it's going to increase its speed. So if we had uniform motion, velocity would be constant over time, and our position time graph would be linear. So it would look a little bit more like this, but linear. However, if we have non-uniform motion, that is, the velocity is changing over time, the position time graph is not going to be linear. And if we look at our position time graph that's shown here, we see it gets steeper as the time progresses. So at the beginning of its motion, I'm going to draw just some lines, what we call tangent, so 90 degrees to the curve. We can look at their steepness. So over time, the lines that kind of just touch the curve are getting steeper and steeper, and that tells us that the cart is speeding up. So its velocity is getting higher. If we look at the same exact motion, but now in a velocity time graph, what we see is that the velocity time graph is linear, so we can fit that line, a nice line of best fit. If this was constant velocity, we would see a flat line because we have velocity on the x-axis, or on the y-axis, sorry. And so because we have this linear graph, we're able to do some calculations with it. Specifically, we can now calculate the slope. And so we're going to zoom in on this graph. The slope of a velocity time graph is equal to its acceleration. So we learned previously that acceleration is equal to final velocity minus initial velocity over the change in time. Now, because time is on our x-axis, change in time is really the run of this graph, and change in our velocity, because it's on our y-axis, is the rise. So that's our slope. And so we can look at this graph and we can pick 2 points on our graph and use those for calculations. So we're going to do that now. So we're going to pick our final point here, just because it's on a nice corner. And so this point is 18 and 180 as our x and y coordinates. And then I'm going to pick this point here because it really bisects a corner nicely. And this point is 6 and 80. So I'm going to plug those numbers into the equation I've written over here. So y2 is 180, y1 is 80, whoopsies, x2 is 18, and x1 is 6. So we end up with 100 divided by 12, and the units on our numerator are centimeters per second, and on our denominator are seconds. And we get 8.3 centimeters per second squared. And if we look at this graph, we'll notice it has a positive slope. So it's pointing up and to the right. That is a positive slope, which means that our acceleration is going to be positive. So our object is speeding up in a positive direction. All right, and last, we're going to look at negative acceleration. Okay, so here we have a cart rolling up a ramp. As a cart rolls up a ramp, gravity is going to slow it down. So if we look at this graph, we see that the slope is pointing down. So our velocity, which is our y-axis, is decreasing as our time increases. So we can find the slope of this graph by picking 2 points that are on the line of best fit. So I'm going to pick this point here, which is 1.8 and 20. And that's going to be x2 and y2. And then I'm going to pick this nice point here, and this point is going to be 0.4 and 68. Okay, so we're going to plug those numbers into our equation for slope. So slope is equal to our acceleration in this case, which is going to equal y2 minus y1 over x2 minus x1. So we have 20 centimeters per second minus 68 centimeters per second. So our velocity change is negative over 1.8 seconds minus 0.4 seconds, but our time change is positive. And we will get negative 34 centimeters per second squared. And so what the negative sign for our acceleration means is that our object is slowing down. So we also sometimes will call this deceleration.